class. Because we have a very short time today, I've decided to do something different from what I expected to do, but we'll carry that because of just the 1 hour that we have. I want to start exposing you to the sort of questions that you will encounter in the exams and see how you are expected to approach them. So that would be my idea. Is very so often I would be trying to give you typical questions, and then we solve them in class, hoping that you start getting used to how to approach different questions as they are, as you meet them in the in examination settings. So let me just share my screen quickly so we can start. I know we have been talking about how to sketch the root locus. Just to emphasize, remember I said we cannot actually plot or draw an accurate root locus except by the use of a computer, that is using a computer tool. Be that as it may, we can sketch the root locus and we can even refine the root locus sketch. So I already provided your class reps with the notes, and I'm sure you already have a hold of them. So there are so many things that I will not discuss because they're already in your notes. I will only look at maybe examples that are not worked out in your notes, or discuss certain other elements that may not appear in your notes. They may or may not appear in your notes, but at least I'll keep referring to whatever content is in your notes. That means I still encourage you to continue making your own notes from our class discussions, because some of the things that I will mention or cover here may not appear in your notes. So we were talking about how we can sketch the root locus, and we got to the point where we were looking at specifically rule number 5, where we have to look at the behavior of our poles and zeros at infinity, meaning we had to draw asymptotes to enable us sort of predict the general direction or the general trajectory of the root locus as the poles move towards the zeros at infinity, okay, or as the gain k tends towards infinity. So in the previous class, when we ended, we sort of drew a sketch, and we said that the asymptotes are not part of the root locus plot. They are simply drawn, they're straight lines that help us determine the general direction of the root locus as gain k tends towards infinity. So they're not generally. So in fact, if you plot root locus on a computer, whether you use MATLAB or Python or whichever software, they will never draw the asymptotes, because the asymptotes are used for sketching the root locus. It's just a technique to help you sketch, but the computer will already inherently have the information to know the direction of the root locus as the gain tends towards infinity. And so the asymptotes will never be drawn in a computer model. It can only be sketched as we draw manually. The other thing that I forgot to mention and emphasize is, please do not, because this I noticed from previous students, do not confuse between the breakaway point. I said we were going to do that today, but I think because of time, I might not cover it. I'll cover it in the next class. We said that the breakaway point is the point at which the poles exit the real axis as they join the imaginary axis. Okay? And the break-in point is where they rejoin the real axis. So when they leave the real axis, that point is called the breakaway point. When they rejoin the real axis, that point is called the break-in point. We'll do an example of that. However, the point of the asymptote, where the asymptote begins when we are obtaining the asymptote intercept, or what we are calling the real axis intercept, this is what we call the real axis intercept. Now, some books will not refer to it as the real axis intercept. I'm only telling you this because you might read different books. Most books will refer to it as the centroid. So if you see that, it's this one and the same point. So the real axis intercept, or the centroid, is the point at which we subtend the straight lines of the asymptotes on the real axis. Okay? So it is not the same as the breakaway point. As you can notice here, that the formula that we used for obtaining the real axis intercept, or the centroid, was given accurately here. This. But we have a totally different formula that helps us obtain what we call the breakaway point. This point here, where the two poles will exit the real axis and join the imaginary axis. So the centroid is never the same as the breakaway point. I hope that is clear. So today what I want us to do, because of the short time that we have, is I want us to solve two questions. And I have already written those questions here, the form of a quiz, but these are typical questions that you can meet in your continuous assessment test, or even in the examination. So I just need you to sort of see how I set my questions and how to approach them in providing the solution. So the first one is a very simple one because it's related to what we have been doing, and it's very obvious in its explanation. It says we need to sketch the root locus and its asymptotes for a unity feedback system, and we are given the forward transfer function. So this is a very simple question. I think you have it in your notes, but it is not solved. So I'll try and solve it here for you, so that when you are revising, you'll be able to know what to expect. So you're provided with G of S. So let's do solution for quiz 1. Now, for those who, I think this is in your notes. The question is on your notes if you have looked at it, but it's not solved. So I'll solve it here. Please don't ask me for the solutions because I'm actually doing this on a screen. So you should be able to draw your own later. I just need to guide you through the process. So to solve this, we quickly do what we were asked to do even in the previous example, where you have to determine the asymptotes, of course, after knowing the number of poles that you have and the number of zeros that you have. So in our case, we have G of S is given by K over S plus 2, S plus 4, and S plus 6. So here, the first thing is just identify the poles and zeros, okay? So we know that we have 3 finite poles. And those 3 finite poles are S equals to -2, S equals to -4, and S equals to -6. Those are the poles that we have. And I told you that the rule for the root locus is if there exists a pole, there must also exist a zero. Now that zero can either be finite or infinite, meaning the location could be finite or infinite, but there needs to be a zero because each pole needs to terminate at a zero. So for example, in our case here, you can see that we do not have any finite zeros because the numerator term, there is no complex number, or there's no zero. So which means that all the poles that we have here must terminate at certain zeros, but those zeros exist at infinity. So we must have 3 infinite zeros, meaning S would be equal to infinity for all the 3. But we do not know their general direction because they can be infinite. Are they infinite towards the left half plane? Are they infinite towards the right half plane? You know, we do not know. The only way we can know the infinite locations or the general direction is by plotting or drawing the asymptotes. Okay, so that's the need to draw the asymptotes. So the finite ones can easily be plotted. But for us to obtain this infinite location we are talking about, we need to get the asymptote lines. So to obtain the asymptotes, you know we have to obtain the centroid or what we are calling the real axis intercept, and we also have to obtain the angles associated with it. So the centroid, sigma A, remember, was the summation of the finite poles, not infinite. Please don't include infinite in this calculation. And the summation minus the summation of finite zeros over the number of finite poles minus the number of finite zeros. Okay? So that is how we obtain our centroid. And in this case, we can see that the finite poles are 3. So we substitute that because it's just the sum. So you have to add them up. So we have -2, -4 added to -6. Then you subtract the number, the sum of zeros. We don't have any finite zeros. The number of poles are 3, the 3 number. The number of zeros, we don't have any zeros. So our solution there should be -12 over 3, I think, yes, which gives us -4. So this is the centroid. But that is not enough. We also have to obtain the associated angles, okay? So the way you know the number of angles you need to calculate is you will see that after a certain point, the angles repeat each other. So you don't have to repeat them. What I mean is we know that to get the angles, the angles are theta. So to get theta for the asymptotes, the subscript A stands for asymptote. So the angles for the asymptotes are given by, remember, 2k plus 1. I can either put pi or I put 180 degrees over number of poles minus the number of zeros. This is just the same as saying, because in our case, we have 2k plus 1. Again, I can put pi or I put 180 degrees over 3. Okay? You know that this can also be written as 60 degrees into 2k plus 1. So you know that k is 0, plus or minus 1, plus or minus 2, and so on. But we are dealing with the positive numbers just for quick illustration. So you can see that when k is 0, theta A, you just substitute for 0 here. So we'll have 60 degrees. When k is 1, we have 180 degrees. When k is 2, we'll be having 4, that's 5 multiplied by that, so theta A would be 300 degrees. When k is 3, we'll be having 6, 7. So theta A would be 420 degrees. So you can actually see that 420 degrees is the same as, because if you subtract 360 degrees, which is 1 full cycle, then this is the same as 60 degrees. So 420 degrees is the same as 60 degrees, which is the same as this. So there's no need to even obtain when k is 3, because it results into 420 degrees, and 420 degrees is the same as 60 degrees. So we only needed k equals to 0, 1, and 2. Then we can plot the asymptotes. So notice we've obtained the centroid for the asymptotes and the angles associated with that, so that we are able to obtain the general direction of the root locus towards the zeros that are at infinity. So we bring in our plot. So again, when we plot, make sure you label properly. This is j omega. And we have 2, 4, and 6. So I'll just 1, 2, 3, 4, 5, and 6. Of course, minus. Okay, so we have poles at point -2, -4, and -6. And the zeros are all at infinity. First of all, we need to know on the real axis, using, I think, rule number 3. On the real axis, where is the root? Where does the root locus occur on the real axis? The real axis segment. So we say that root locus occurs to the left of any odd number of poles or zeros. So we start beginning from the rightmost. So this is pole number 1. So if it is pole number 1, because 1 is an odd number, to the left of it must exist a root locus. Then we have pole number 2. 2 being an even number, it means to the left of that pole, there is no root locus. Pole number 3. Pole number 3 being 3 is an odd number. So to the left of that odd number pole, we must have a root locus. And remember, the other rule was the root locus must leave the pole and head towards a 0. So in this case, we are leaving the pole and heading towards a 0. And that also applies to this other 2. You leave the pole towards a 0. But we do not know the exact locations of the zeros. So the asymptotes will help us do that. So what is the centroid or the real axis intercept? It is at -4, meaning at -4, we can draw, I'll draw it in green because it's not part of the root locus. At -4, we have a 60-degree angle. So we can sketch something to represent 60 degrees from -4. Then 180 degrees. So remember, it's just a line. So I need to draw a 180-degree line here, but I don't need to draw it because we already have the real axis, which is a line already. So that will guide us. And then we have 300 degrees, which is about another point towards that direction. So the asymptotes are already drawn for K is 0, for K is 1, for K is 2. Because you realize if I try and draw 420, it will still bring me back to this line of 60 degrees. So it's the same thing. So this tells me one thing. Number one, it tells me that because I have 3 poles, I can already see that the pole at -6, there is, when K is 1, we have 180 degrees. So it means that the pole at -6, being on the real axis already, will terminate at a 0 that is also on the real axis, but at an infinite location. So here, the gain K, when this pole begins its trajectory, the gain is 0. Then it will just move along this straight line, and we assume that this line, the root locus lies to the left all the way to infinity. And at infinity, the gain will be infinite. Now, we have 2 poles left, at -2 and at -4. We said that these poles, because they are like poles, they repel. So it means they'll start their journey, but at certain point that we call the breakaway point, they will leave the real axis and look for their respective zeros. So the plot for the root locus would be one pole will try and follow the trajectory of the asymptote closely, but not touching. The other one will also do, because of the symmetry rule that we talked about the imaginary line or about the origin. So again, it will move, but not touching, okay? So, and then, of course, you have to draw the direction like that, to show that that is the movement, okay? So that becomes the plot for the root locus. Now, remember that for this kind of plot, it is a sketch that we have done with the aid of the asymptotes. If we were to do this in MATLAB, it will not provide the green lines. It will just provide the red lines. And then if we were to know the number of branches, we would know by counting the number of closed loop poles. But even in our plot, we can see that this is one branch. There's a branch towards that direction. It's because each branch we defined it as the trajectory of each pole. So if, let's say, pole at -2 will get to its breakaway point and then move upwards, then that's another branch. If the pole at -4 moves and gets to the breakaway point and then moves towards the 0 at infinity, that's another branch. So we can actually say that here we have 3 branches. we have 3 branches because one corresponds to the trajectory of each of these poles as they head towards infinity. And those branches you can see corresponds to even the number of poles that we have for the open loop. The reason why the number of poles here, because the rule, if you remember what the rules we did, was that the number of branches is equivalent to the number of closed loop poles. But these, remember, are open loop poles. But they're equal to the the number of open loop poles here are equal to the number of closed loop poles because we have a unity feedback system. So it means if we have a unity feedback system, then we only have G of S to worry about because the feedback is just unity. So even if I got the closed loop transfer function, I would only have it as 1 over 1 plus G of S because the H of S is 0. And therefore, the number of poles will not change. The number of poles and zeros would change if there was H of S, and H of S is also probably a 0 or it's a full transfer function. Okay? So, but because the H of S is 1, it's unity feedback system, then the number of closed loop poles is just equal to the number of open loop poles. So that's just a hint on the sides to let you know. But ideally speaking, ideally defining it, we should say that the number of branches in a root locus equals the number of closed loop poles, okay, of its transfer function. But because it is a unity feedback system, we can still use the open loop transfer or the feed forward transfer function to know how many poles we have. That will tell us the number of branches. Because if you're sketching, you just need to know how many times will I have to branch. Pole at -2 will branch once. Pole at -4 will also branch once. And then the pole at -6 will go straight to infinity. So that is how I expect the question to be solved, okay? So that should make sense. Good. As simple as that. Now, the question might not be as simple as this in the exam, but the concept is the same. Meaning, I'm not saying I intend to make it very difficult, but I'm just saying the transfer function could be a little, I might give a transfer function where you have to find these roots yourself. I don't find them out for you. So maybe I'll just give you a third order system. You use your calculator, obtain the roots, and then that gives you your poles, and then you proceed. Everything remains the same, okay? So I'll not serve everything on a silver platter anyway, at least just to make sure that you are tough enough to encounter problems out there. Now, another typical question, this I think I took from the last year's exam question. It says, given an open loop transfer function, so again, you've given an open loop transfer function as shown there. It's a 3-part question. It says, 1, you need to identify the number of branches in the root locus and the regions of the complex plane they cover. So always make sure you read the question twice to know what is required. Maybe one question requires 2 things. Like in this case, we need the number of branches in the root locus and the regions of the complex plane they cover. Meaning, what regions, because a complex plane or an S-plane has 4 quadrants. So what regions are covered by the root locus? Number 2, sketch the root locus plot for the system, as of course the gain varies. And number 3, briefly discuss the effect of changing the location of a pole on the root locus. So number 3 is a general knowledge question that expects you to know the effect of moving either zeros or poles in a root locus. So if you're studying, you must try and figure out what is the effect of moving a pole towards the origin or moving a pole away from the origin? What is the effect of moving a 0 towards the origin or moving a 0 away from the origin? Those you need to understand. The effect is based on the performance. What effect does it have on the performance of your system or of your closed loop transfer function. Okay, so let's start by solving this for the few minutes that's remaining. The question is pretty straightforward. Again, before we sketch the root locus, so let me just write the question again. So the G of S is given by K over S into S plus 1, S plus 2, S plus 4. Okay. Now, again, I told you in an exam setting, the denominator term could be given in its fourth order. So you have to simplify for yourself, or you have to factorize yourself. But these days you have calculators that can do that. Anyway, so the first question was asking us, 1, identify the number of branches in the root locus and the regions of the complex plane they cover. So how many branches do we have here? So you can actually see that we have 4 finite poles. They are S equals to 0, S equals to -1, S equals to -2, and S equals to -4. And so we expect to find, we don't have any finite zeros, but we just expect to have 4 infinite zeros, so that each of these poles can terminate at those infinite zeros. So S equals to infinity, because we don't know where they are, in what quadrant they exist, but the asymptotes can tell us. So based on the definition, the strict definition is that the number of branches in a root locus must equal the number of closed loop poles. This being a unity feedback system, we could still use the number of open loop poles to know the number of branches. So you can actually solve the first question by saying, this is what I expect, that the open loop transfer function, the open loop transfer function, G of S, has 4 poles. Sorry, not 4 poles, 4 finite poles. Finite poles. Then you say the number of branches, the number of branches, the number of branches of the root locus, okay, is equal to the number of poles. In this case, because it's a unity feedback system, you can say it's equal to the number of poles of G of S, which is 4. Okay, that is the solution to that part. The other one says we need to identify the regions where the root locus lie. But the regions are expected to be on the, we mean the regions of the complex plane or the S plane. Okay, S plane is called a complex plane because S is a complex number. It is alpha, it's sigma plus J omega. Okay, so that's why it's called a complex plane, because S itself is a complex number. Okay, so what regions are covered by the root locus? A quick sketch, you'd see that you'll have a pole there, you'll have a pole at somewhere -1. We've not sketched it yet. Another one at -2 and another one at -4. So clearly you should see that there will be a trajectory of these two poles, then they leave the real axis. Then these other ones will also move and then leave the real axis. So you can actually just say by observation, okay? So by observation, this is the second part of that question one. By observation, you can say that each branch of the root locus starts at a pole, and terminates or ends at a zero. Each branch should start at a pole and end at a zero. Okay? So in our case here, the root locus covers the entire complex plane, except for the region to the right of the poles. So it means that you will see that this region to the right of the poles, there's no root locus, because even on the real axis, we say the root locus will exist there because this is odd number. This is number 2, so there's no root locus to the left. This is number 3, so there's a root locus to the left. So you can see that the root locus is actually to the left side. So the root locus will cover the entire region to the left of the poles. It will not cover the regions to the right of the poles. Okay, that's just by a quick observation. But now the second part of the question requires us to plot the root locus. So now it should be very easy to do a plot of the root locus, because you see, in our case, you've determined that you have 4 finite poles and you'll have at least 4 infinite zeros where these poles will terminate at. So to obtain them, so for part 2 of the question, you'll need to obtain the centroid. And by now you know, so the centroid would be summing up these things. So we'll be having minus, so we'll be having 0, minus 1, minus 2, minus 4. 0 minus, is it minus 1? It's 1, 2, 4. 0 minus 1, minus 2, minus 4. Then the summation of finite zeros, which we don't have finite zeros, over the number. Here we have 4, and the number of finite zeros is 0. So you'll be having, this is minus 7 over 4, which is basically minus 1.75, hopefully. If I'm wrong, please let me know, because I'm doing this off head. So minus 1.75 is the centroid. That is the centroid. And of course, the angles would be 2k plus 1 into 180 degrees over 4, which is the same as saying 4 goes here how many times? 45. So it would be 45 into 2k plus 1. So when k is 1, theta A is what? It's 45 degrees. When k is 2, theta A is, we have 3 multiplied by 45. Is it 3? When, yeah, it's 2. When k is 1, no, I forgot when k is, this is when k is 0. When k is 0, you have 45 degrees. When k is 1, please don't make me mislead you. When k is 1, you have 3 multiplied by 45. 3 multiplied by 45, I think that should be 135 degrees. Then when k is 2, we have 5 multiplied by 45. 5 multiplied by 45, it should be 225 degrees. When k is 3, we have 7 multiplied by 45, that's 315. In fact, 315 degrees 315, no, yeah, that's still fine. That's still not the same, okay? 315 degrees. When K equals to 4, for example, theta A would be having we'll be having 9. So 45 by 9. So that would be, I think that would be 405 degrees. 405 minus 360, that should be 45, yeah. So we don't need the last one. So this last one is the same as the first one. This one is the same as the first angle, so there's no point for that. Anyway, so now we can plot because we know the centroid and we also know the angles. So we can actually plot our root locus like that. Sigma j omega, origin -1, -2, -3, -4, -5, -6. So we have poles at 1, 2, oh, we only have them at 1, 0, 1, 2, 4. Okay, so 0, 1, 2, and 4. So real axis segment, we know that a root locus exists between these two poles. And this is number 2, this is number 3. So there's a root locus also between these two. The asymptote says it is at the centroid is -1.75. So it is somewhere just before 2. Then you have to draw a 45-degree angle there. Then the next one should be a 135-degree angle, 135, so it goes like that. Then 225, like that. And then 315, like that. Good, yes. So that means, therefore, that these two poles, the one at -0, the one at 0 and -1, will break away at somewhere in between. Then we'll try and move towards one asymptote, the other one in the opposite direction, like that, with an arrow going like in that direction. Then these two other ones will also break away somewhere in between. Let us say they break away at -3, then this will have to go in that direction. Notice they don't touch the asymptotes. So in that way. So whatever appears in red is what the root locus is. Whatever appears in red is what the root locus is. The green is simply the asymptotes. In fact, it is encouraged that in class, you might not have, as even in an exam setting, you might not have several inks or colors to use. So you need to label, like you can say that is an asymptote. It is not a root locus. So everything else will be assumed to be a root locus. So for the asymptote, you must say that it is an asymptote. So I'll not consider it as a root locus. So this is an asymptote. Even this one is an asymptote. Everything else is the root locus. Okay? So that is the plot for that question number 2. So you can see that in this question, there's a general direction of the root locus towards the left half plane and another direction towards the right half plane. However, because the root locus will terminate at infinity, anything beyond that, the root locus does not exist in that direction. Okay? Now, the third question was, if I go back, the third question was, so we've sketched the root locus as the gain varies, yes. Briefly discuss the effect of changing the location of a pole on the root locus. This is a very important question, knowing the effect of changing a pole on the root locus. So I think I will take some time again in future to give you certain examples. And I think that also exists in that book by Ogata. Okay. a control systems engineering by Ogata. It has a very good illustration of what happens whenever the poles move towards the origin and when they move away from the origin, and also when the zeros move towards the origin and when they move away from the origin. However, this is how I can attempt that last question. You can say, because there are so many effects, the effects that poles have on the root locus are so many, okay? Discuss the effects. So you just don't mention, you discuss the effect of changing the location. So I can subdivide this into categories and say, the one obvious one that we all know and even we have covered before is stability. That is one effect. Okay? So we can say that moving, because this is because it is discussed, so you must explain the effect of changing the location of a pole on the stability of your closed loop system. So moving a pole towards the right half plane or towards the origin can make the system unstable. Yes, moving a pole towards the right half plane can make the system unstable, since poles in the right half plane, indicate, we mentioned this in the previous class, that the system's response grows exponentially. The system's response grows exponentially over time. Okay? So you have to also say the converse. So conversely, you have to say, you don't just mention one side and then you leave it there. So you can say conversely, moving a pole towards the left half plane increases stability. Okay, of the system. Let me use the same wording. Since poles in the left half plane, indicate bounded and decaying responses. Indicate bounded and decaying responses. If you did your controls in fourth year properly, you remember bounded input, bounded output. Okay. Anyway, so basically what we mean is, if you are to plot a transient response, don't plot this, I'm just giving you a brief, that when you're plotting a response of a system, you will see that if you're moving a pole towards the right half plane, then your system has a large overshoot and takes a longer time to do what? To decay. Okay. So you can see that this is the maximum overshoot. Okay. So it's very far away from here. Okay. And so because that pulse is huge, the settling time is longer. So, but if you have a system, if you move a pole towards so this is over time. If you move a pole towards the left half plane, then what you will have, actually I should draw it on the same scale here. What you will have is a system that sort of decays faster. Okay. So this, you'll notice, so this is the right half plane pole. Okay. And this is the response for the left half plane pole. So you can see that the overshoot for the left half plane pole is smaller. The settling time is faster. So the system stabilizes sooner rather than later when compared to the right half plane. Okay, that's what we are trying to say. Transient response was done by you in the previous class, in the previous year. So that's not my part. I'm just trying to bring it up to speed. So just like I've said, whatever I've said, you can put it in words and say it like this. Maybe I can put it in words because we are supposed to discuss. So we've discussed regarding stability. So you can also discuss regarding transient response and say the following, because I'm here to help you see how you can respond to questions. So under transient response, because that's another effect that moving the location of poles have on a closed loop system. You can say poles closer to the imaginary axis like I've said, results in oscillatory behavior and higher overshoot. Because you can see the one on the right half plane, or the one that moves towards the imaginary axis, oscillates a lot. It oscillates a lot and has a higher overshoot. So you can say while, because you have to say both sides, while poles further away from the imaginary axis, okay, just say left half plane, okay, lead to faster settling time. Please mute your microphones. Leads to faster settling time and lower overshoot. Okay, so that is how you would probably respond to such a question. So you have indicated the effect of changing the location of a pole on the closed loop system based on the stability and also based on transient response. You can even go further and indicate the effect on frequency response. This you should have also done in your fourth year. Frequency response. You have a very good teacher in Mr. Fariz, so I'm sure you could have mentioned under frequency response that, of course, the location of poles will influence the frequency response of the system. Including, when I talk about frequency response, I talk about things like resonance frequency, bandwidth, so that poles closer to the imaginary axis will correspond to some dominant frequencies in the system response, while poles that are further away will contribute less to the overall frequency content. Okay, so that is another factor or another effect, but I'm only interested in the transient response and the stability. In fact, stability is much more important than the transient response. Then you can talk about frequency response and the likes. Okay, so that is typically how I expect the question to be solved. Okay, now let me check the time. We have 7 minutes. Any questions? Because now I will end the class and say that in the next class, I expect that you read the notes on, how is it titled? I think it's titled refining the root locus. I think so. So that here I need you to go and study on the breakaway points and how to determine it. Please go and study that, because I will assume a lot of things because you already have the notes. The break-in points, okay? Remember, you can have more than one breakaway point and more than one break-in point based on the number of poles and the number of imaginary poles and so on. And also on the J omega axis crossing, another important one. So notice the first 5 rules that we did, rule number 1 to 5, helped us do a sketch of the root locus. But we'll be having a set of other rules, and basically they're going to be 6 to 8 or whatever, but they'll help us refine that sketch, meaning the sketch would be more detailed. As it is now, if you look at this sketch here, it is not as detailed as expected. Why? We do not know what this point is. We also do not know what that point is. We need to know them. We do not know what this crossing, at what point is this crossing? What is this value? It's J watt. And what is this value at this crossing point here? Minus J watt. That's what you, so these are the J omega crossing. This point and this point are the points that it crosses, the root locus crosses the J omega axis. So we refer to those points as J omega crossings. So for the root locus to be more accurate, we need to indicate what value these are and the corresponding value of gain, so that you know that any gain beyond that would lead to instability. Okay, so if you know the gain at exactly the point of the J omega crossing, in your design, you ensure that you don't exceed that gain, because if you do, then the trajectory would head towards the right half plane, and that would lead to instability. So we need to know the J omega crossing. We need to know the value of the gain corresponding to the J omega crossing. Then we need to know the breakaway points, like that point there and this point here. We need to calculate those points, okay? If the poles were traveling, let's say the poles were traveling from the imaginary axis and coming back, you know, if they were coming back like we had plotted here. I think we did one in the previous class. I need to show you that. Yes. So you see, these ones left and then they moved and then came back. So here, the point they break is the breakaway. The point they join in is the break in. So you need to calculate this point. We need to know what value it is. And we also need to know what value it is here. So in this case, we don't have J omega crossing. Luckily, our root locus here does not include the J omega crossing. Everything is on the left half plane. But we need to know what the break in point is and what the breakaway point is. Okay, so that is what we'll be doing in the next class. I will not be showing you the principle because you have the notes, but I will be doing examples that make use of these calculations. So I'll be referring to those formulas that are given there. That is why I expect you to go ahead of me and study, so that when we do examples, you'll be able to follow through, so that I can move quickly and move on to the design. Remember, now we have not started designing anything. We are simply sketching. We're simply trying to see how we can use the root locus. And then later we get into how we can design control systems, making use of these root locus techniques. So the design aspect will come later. Good. So that marks the end of our discussion today, ladies and gentlemen, and maybe for this unit, it marks the end of our discussion this week. So I hope that we'll meet again next week as we proceed with our classes. As it is, I'll stop sharing unless there's any question from the class. I encourage you to talk to your colleagues to ensure that you attend as many classes as possible. I am taking attendance because